wave reflecting and undergoing superposition, we can have what we call stationary waves being produced. Here's an example of stationary waves that being produced when you have both ends fixed. The first one is called the first harmonic or the first overtone. Okay, second is second harmonic, and so on, right? Here's an example: second harmonic, third harmonic with both ends fixed. Anybody remember? They always increase by what? Huh? Half a wavelength, right? As they go from one harmonic to the next, they always increase by half a wavelength. Suppose you had one end open, right? Suppose you had one end open, the waves look like that. First harmonic, second harmonic, third harmonic. Remember, we could also call them fundamental. We could also call, sorry. We could also call them fundamental, first overtone, second overtone, but they all increase by half a wave. Okay, regardless of how they are produced, right? As you go from one harmonic to the next, they always increase by half a wave. Here, this one is what? This is when two ends are open, right? Always remember, when the ends are open, you have an antinode. When one end is closed, you will have a node. Okay? If both ends are open, then you must always have antinodes on each side. Please remember, as they go down, they always increase by half a wave. Okay? So those are the things that we did last day. I also showed you how to work out the frequency of the incoming harmonics. That's okay? So using the formula, F is what? F is equal to V on lambda. Okay? Normally V is given and lambda is what you have to work out. All right, so we want to take a look at how to perform some calculations on these stationary waves, right? Let's do a few and then we're going on to wave phenomenon. All right, let's take a little reader. Right. So another stretch string is used to form a stationary wave. A part of this wave at a particular instant is given in figure 3. The points on the wave are at the maximum. What's the phase difference? What's the formula again, Javed? What's the formula for phase difference? Look back page fast. What's the formula for phase difference? X over lambda by 2 pi. Nice. So we'll go to X there from this. Oh yeah, work it out fast. X over lambda by 2 pi. X is from here to here, right? X is from there to there, use their scale. Use the scale that they gave you there. Hold on, yeah, that's an answer. Okay. Use their scale, right? Just use what they give you there. 1 is 1, 2 is 2, 3 is 3, 4 is 4. Let's use Talia. Huh? How Wednesday? Okay, what are it? How long it take? How long it take? 2 hours? How long? Hour 60 minutes? You walk it? 60 minutes? No. I'll just move it. Right. How much you get for lambda? Well, 12 centimeters, 12 blocks. What look at that? 12 blocks. So yeah, let's see how much blocks is the one thing. That's 1, 2. 1. Olio, hey, Olio, hey, please. Well, relax a little bit, do all this now. 1, 2. Darion. So this is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Right? So we're going with lambda 12, right? X to Y is how much blocks? X to Y is 2. So we will put 2 on 12 multiplied by 2 pi. Right? Leave the answer in terms of pi. So that's 1, 6. So I got pi on 3. That's the answer. What is it? What the P is different between X and Y? Right? Yes, sir. Right, so the P is different with that, right? Anybody get our line? Pi on 3? So it's 1, 6, 2 pi, right? Which should be pi on 3. And the formula for P is different. Yes, sir. Now we didn't know this.
Say this is not in my notes. It is not in my notes. You see it,
Right? What's the difference between a node and an antinode? Huh? No. That's what happens. But antinode is what? Maximum displacement, and I know this. Zero displacement, right? Right, so a node, antinode. There's an antinode here, and there's a node here, right? Right, that should be seen, it's too good, but we just doing part here alone. Right, we just doing part here alone. Oh wait, no, we can do the whole thing. We can do the whole thing. Alright, Collier, hey, let's pass now. So figure 2, in case you're not seeing, figure 2 shows a stationary wave on a wire on the tension. The frequency is 1200 hertz. If the length of the wire is so much, find the speed of the waves moving. Right, and let's zoom in a little bit more. You have the length of the wire there, and you have the frequency. They want you to find speed. Put it out, send your answer, please, online if you get it. Question say find speed, and that's what they give. Length and frequency. Shidana come to pick you, right? Yeah, pick it up quick. Don't let Jabba distract you. Hurry up. Sylvester, come on, hurry up. Hurry up. Go. I swear this. Yes, sir, yes, sir. We can tell you manage to, because you said on next one. You work out this?
Yes, anyway.
You work it out?
Yes, sometime.
So what we use to define speed? V is equal to what? Right, V is equal to F lambda. We already have what? We already have F. Right, so you have to figure out now, if the length of the string is 4 meters, what is the wavelength? Work it out, message the answer. Sorry? That's the length of the string here. That's how long the string is. You have to figure out what is lambda. Huh? Yeah, we continue from last week. So V is equal to F lambda. So what's the length of this string again? So on that diagram, 0.4 is some way away. Right? So from here to here is 0.4, right? You have to figure out now how to get lambda. Look, Mark, he's guys already. Don't know if it's right, but you get it. You have something. Right? You already know the frequency, you have to figure out what is lambda. Right? And his answer looking close to correct. Close. Get ready, yeah. Right now. Right, well, this question belongs to Shazana, so you waiting on Shazana. Yeah? So Shazana, help me out now. How you got lambda? How you get 0.2 for lambda? Okay, right. So if you look at that diagram, there are two wavelengths. You see that? Now, yeah? Right. So it have two wavelengths, and two wavelengths is 0.4. See two cycles there? 1, 2. Right? So therefore lambda is 0.2 meters. So V is equal to 240 by, sorry. So V is equal to 1200 by 0.2, which is 240 meters per second. With the 5T, right? Part B. Am I right then? So what's the right answer? Yes. Right, next part. Here's what they want. We'll go to the formula after, right? Part B is right here. What will happen when the speed of the waves moving along the wire? If the tension is doubled, all other factors remain the same. The length is doubled, all other factors remain the same. Right? Before you start to try to figure this out, go back to the notes, go back to the handout, and I gave you a formula for speed of the wave on that on the wire. Tell me what it is. V is equal to what? Huh? No, not F lambda. That's the next one. V is equal to F lambda is one formula we did that in part 2. But there's a next one that you're gonna need part 2. Huh? No, not that one. And next one is to do with your tension. Okay, let's go right back to stationary waves. Right above, same thing that we're reading that's now. I want to make sure you all know it there. Right, yeah. V is equal to, right, and square root of T over mu, right? And T is what? T is tension and mu is what? Mass per unit length, right? It's called mass per unit length. Nice. So here's what happened. Look at the formula. For this part, you need the formula. They said tension is doubled. What will that do to the speed of the wave? Tension is doubled. What will that do to the speed of the wave? Look at the formula. It will increase the speed by how much? What's the formula here? If you were to double tension, right? Well, when you factor it out until you get root 2,
Yeah.
right? So therefore, the speed will increase by a factor of root 2. The speed will increase by a factor of root 2. Question, length is double. If the length is double, what will that do to this speed, you can use formula 1 or formula 2. If the length is doubled, what will that do to the speed? Use your original formula, that'll be easy. Go back to what they had here. If it double the length there, think of what will happen. I pick somebody online, Marquis. I think Marquis.
Well, I think.
Yeah, here, sir. If it double the length, go back to the first example. What would happen?
Take a brick, get up.
Yeah, we shouldn't call it, right? So we are lucky. Finish. Yeah, Marquis, what will happen? Think of the first example. If the length was 0.8 instead of 0.4,
Take a double. Right.
so that was double lambda, right? Lambda becomes double, so therefore speed becomes double. Huh? Yeah, if it double the length, you'll double the speed of the wave. Next part. See if you can answer this now, please. Right, actually, we can do this together because I might take too long. Right? They said E naught is the amplitude, lambda is the wavelength, lambda here. F is the frequency, and they give it this formula here. They want you to say what is amplitude, frequency, wavelength, and speed. Right? Let's start with phase. Phase was the amplitude in that. Let me just zoom in there. Look at the equation here, phase. While I wasn't paying attention, we went to the equation. What there is amplitude? Yeah. What's amplitude, phase? Look at the formula. 5 density. Okay, correct. Wavelength. What's the wavelength, Jacob?
Sorry.
Sine, you say. Huh? Right, so what is lambda? What is lambda? Papi. What's in front of x is what? In front of x is 2 pi on lambda, right? What do you see in here? So 2 pi on lambda equals to 740, right? So lambda is how much? Right? The lambda is 2 pi on 740, right? Nice. How much is that? What is 2 pi on 740? 8.49 by density minus 3. Next, frequency. From that formula, what is frequency? Darian? Huh? Don't come here. Oh. Darian, frequency. Look at the formula. Oh God, it's the same thing we use. What is the frequency? So look at the formula, sir. And which part of the formula have frequency in front of what?
And then front of Y.
Front of T, right? From the T is the frequency. You sure?
Yeah,
So can I compare it here?
yes.
So frequency is equal to 251,300 divided by 2 pi. That's okay, so I just compare them down here. That was all.
Go to.
That was all down here. How much is that all here? 39,000. Right? Work out the speed fast now, come away again. Work out the speed of the wave. Work out the speed of the wave. Hey, Mr. Philip, run the whole thing. Hey, man, you run it. Five big real bad. Oh, 1.5 feet extra.
Yeah, but I don't.
I show you. Vaya, cara. Right, so you're using V is equal to what again, Kevin, to work out this? V is equal to F lambda, right? How much is that? $339.6. Katrina got 339.6. How many got 339.6? 339.6. 339. Online, are you okay with that? Reese, Kalina, are you okay with that?
Oh, we do.
Next one. Right, this one has a little bit different, same principle.
So, one of the 399. So why is it?
Where I am.
Your house. You come here, no?
Try this one here, Olivia. Try this one here. I want to zoom into the question, right? But I see there's a tuning fork now. So what? The little thing on top of the tuning fork that produce the wave. One end open, one end closed. Okay? But I'm gonna try to focus on the words here for you, right? Work it out. You all know what the answer is supposed to look like, but try to work it out. Let's see if we'll get an answer first. Oh yeah. Oh yeah. Try that, please. You don't know what the answer is because they asked you to speed us up. Oh. Yeah, so it's around 350 somewhere, right? But let's see if you can actually calculate that. What do you guys? I can barely see that much stuff. I didn't know that. I feel like I just clear up the area, you know, I was trying to get like a black and white stuff. Alright, let me go finish. So they gave you the frequency the tuning fork operating at, right? They gave you the frequency the tuning fork operating at. They wanted to find speed, so P is equal to F lambda, right? We know F, we don't know what is lambda. We know what the answer is. Technically, you can kind of go backwards, huh? Yeah. But you don't want to go backwards because you know your work, right? So a tube can excite the column of air above the water, whose level can be changed by tap at the bottom of the tube. As the water is drained out, the sound intensity is enhanced. So enhanced means that resonance or stationary wave. When its length is 0.6 and again when it's 1, right? So they went from one harmonic here, they didn't tell us which harmonic, to our next harmonic here. What do we know happens between harmonics? But watch out, you didn't tell him. I see every phone on here after. Okay. Tell me now. Between harmonics, what has happened? I told you to make a note of that. Something always happens between harmonics. Don't start the nine same class. Well, just do polyname now. Let's leave them alone. Yeah.
No, guys, not me.
What happens with what? All right, wait. That's the same one. Yeah. Anybody between harmonics, something has always happened. You don't answer me. As a message. Got you. Yes. Huh? Yeah. Now, something else I'm looking for.
So between them
We're trying to find lambda, right? So the hint is, how does that help us find lambda? From one harmonic to the next, what is always happen? Yes. Where's that, Chitana? You added lambda too. So if I go from 0.6 to 1 meter, that extra what? What's the extra there? That extra 0.4 is how much? It's half a wavelength, right?
Yeah.
Every harmonic we keep increasing, right? A lambda.
Yeah.
Are we okay with that? So if you go from 0.6 to 1, that should be an next half a wavelength. So it means that 0.4, it means that 0.4 is equal to half a wavelength. So a wavelength is equal to 2 by 0.4, which is 0.8.
Which is,
So therefore, V is equal to 0.8 by 440, which should be close to 3 something.
you can explain that again.
That's not. That's not right. What's that?
Yeah. Take it again.
Just not just tell me the value there. 0.8 by 440 is how much? 3? 5. Yeah, over here. Right. So here's what they observed, right? As the water was drained out, a sound intensity was enhanced. Enhanced means that's resonant to a stationary wave, right? So you observe your first stationary wave at 0.6, and then they observe it again at 1. So it means that one harmonic occurred at 0.6, and then the next harmonic occurred at 1 meter. And we know from one harmonic to the next, it always increases by what? It always increases by half a wavelength. So therefore, 0.4 is half a wavelength. So therefore, lambda is 0.8. Right? So once you observe that this is one harmonic to the next, you know that there's half a wavelength in between them. Okay? Are you okay with that there?
Yes, sir. Actually, on this.
352. Let's go again.
So what's it?
Right, next one.
I know.
Do part C. I think better get 2 minutes. Do part C, that's 2003.
No, I don't understand. That's not nice.
Same thing is decided.
So ends. So you just have to speak with them.
Oh yeah,
It just comes.
you do one answer?
Why? Why? Hey,
I think point dummy.
say you're talking about you guys.
Oh, that was not so.
Yes, sir.
Which one was that?
Moving.
Oh, no, I'm saying around with something.
You was, yeah, that big mustache too.
I didn't know that. We were in 3 games today.
You play?
Yeah, I think about. Yeah, but.
Yeah, I thought they have a need or something.
Yeah, so I think. Huh? I still going to nothing. Huh? It was actually that research.
Yeah, it is easy.
Actually, no, it feels bad. So it's better classification. That's true.
Say I do next week.
Yeah, it is true.
Yeah, they answer next week.
After how about you? Let me do that. Oh, I do something else. Yeah.
Sorry.
I try all kind of things.
So.
Oh yeah, do that part, see that. You listen to that. Yeah.
Still wait, why is the only one that is supposed to have it?
But except other things on it, I use my phone. My phone. I know, but kids are things, but that was all I know. Which one? Yeah, what I, that is my phone.
So you don't run in school? Yeah, no. You didn't run everything.
Excuse me, or if you pass, please.
It'll be so nice if you in the video, okay, and like, yes, you came back. And you're gonna be swearing like.
But let me hurry up, please. Hurry up, just do the part C. Come on, we still have some more things to read out, right? So whatever we have now, boy, just one more question, man, to do. Ignore part C, because it's taking too long, just part one and top alone. Right, calculate the length at which a tuning fork would produce resonance. Right, you're kind of working in reverse here to the last one. Alright, there you go, that's the best stuff.
So, yeah, this, yeah,
You know, B is equal to F lambda, right?
I say, you have B, and you have F, and you want to find out, so it's going to be on F.
So you find lambda, alright,
Yeah.
alright,
All
right. That's not right. So yeah, so when you found lambda, you got 340 on 280, nice.
Which is approximately 1.2 meters.
1.2 meters, nice.
And
Right.
that's the extent of what we're getting.
Okay, so at least you have something. So Its length may be 0.5 to 1.8. Calculate the length at which a tuning fork would produce resonance. So the egg column is forced, one end open, one end closed, right? So the first harmonic, when will you hear the first harmonic? How much of a wave? Look behind the diagram. One end open, one end closed. First harmonic for one end open, one end closed. How much of a wave is that? Quarter of a wave, right? So that's quarter lambda. So find quarter of 1.2. Tell me what you get. Quarter of 1.2 is 0.3. Can you observe that first harmonic between what they gave you?
Yeah.
Can you observe it?
Yeah.
Javid, can you observe the first harmonic?
No, you can't.
No, you can't because it's too small, right? Right. Without doing any, well, you do a small calculation, right? When will the second harmonic be heard?
That's 4.6.
Keep on that.
3/4 of a wave. Why? Because you add in?
Ah,
Right.
what?
So find 3/4 lambda. Find 3/4 lambda, what you'll get.
Yeah.
0.9. Will you observe 0.9?
Yes.
Yes. Right? So they wanted to calculate the length, you'll observe that. 0.9. Work out the rest. Work out the others. Sorry, sir. Well, work it out, sir. Work it out fast. Find the other time. Right? Please, what you get? Well, you could have one P.
Yes, 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 yes.
How will you talk? Third harmonic is how much of a wave? 5/4 lambda, so that's 514 by 1.2, which is how much? 1.5. Any more?
That's all.
Well, when will the fourth harmonic happen, Jacob? When will the fourth harmonic happen? Which is?
No, it's right. We plus the 5.4, right? They get on. So.
So that's 7 and 4 by 1.2, which is how much? 2.1. So you can't observe that, right? You can only observe 1.5 and 0.9. Are you okay with that? Kazana, you okay with that? Marquis, Kalina, you all okay with that? Viraj? Alright, so we have some notes to look at now, right? Ready? Yeah, but close the door. Yeah, but I'm closing the door. What do you want? Hi, I'm here for.
Yes.
One to go that door.
Why? We never see what we watch you.
Next. I have door. Oh, the same picture I take, alright, nice. So that is yours. That's the way you handle stationary wave type questions, right? You have a next one again that came recently, but it's taking too long.
Do it now, sir.
What are the linemen there? What? Yo, mark on them there. And run it, go it and share. We had it good. That's it, yeah, that's what. Yes. I know, I think with some of those now, take too long.
Yes.
I mean, can't see some good, I
AC catch relation in 4K, right?
there were.
What? What do you think?
Yeah, but then close the door, good, yes. Alright, so I want to just go through some things from form 5. Let's take a look at the wave phenomena.
And,
Yes,
Huh?
I don't go to course, me, I get it.
Alright, I told you, I didn't like to answer this now. All these things are things that we did in form 5, right? What are the 4 things that waves undergo?
diffraction, interference,
Diffraction, interference,
reflection.
reflection, and refraction. Okay, so we just we run through these things, right? Reflection, we have the laws of reflection. All the rays lie on the same plane. The angle of incidence equal to the angle of reflection, right? We have to remember also that the angle of incidence equal to the angle of reflection. Refraction, on the other hand, the incident, the refracted, and the normal all lie on the same plane. In refraction, there's a change in direction of the travel of the wave, and also there's a change in speed, okay, and a change in wavelength. But what remains the same fate? What remains the same? What's that? When I to lock the door and go inside. Yeah, but put in the door, man. Put the bag on, go that door. Yeah, I know that one. Right, so refraction, you should remember that, right? There is an increase in wave. Here's an example, moving from one wave to the next. Right, anybody remember the relationship? Oh, I don't have it here. But what's the relationship that shows you how much refraction will occur?
Sin and what kind of.
What is called a law?
Oh, there is.
Snell's law, right? Sin theta 1 over sin theta Two. That's okay? That is Snell's law, right? And it could also be speed in medium 1, speed in medium 2, lambda 2. Or, right? And we will focus on explaining this in a little while further. Right? So basically bending of the wave. Anybody remember what is called when the wave travels along the normal? Sorry, along the boundary. What is called this pressure angle here? Critical angle. And if you exceed the critical angle and the wave inside here, so wire passing down outside the toilet. That's not inside the bathroom. Inside the bathroom is next. Right, next. Next it will be diffraction. Right, diffraction is the spreading of a wave. Right, which is limited by the obstacle gap. Diffraction is the result of superposing stationary waves from coherent sources on to the other. Right. What would make the diffraction? What will make the diffraction more pronounced?
If it's smaller, think smaller.
What's smaller?
If these it's smaller.
The opening smaller, right? So which one do you expect the larger amount of diffraction? Diagram 1 or diagram 2? Which one will cause the greater diffraction? Diagram? Alright, let me relabel it.
No, so I would say that.
One on top, 2 underneath. Which one will cause the greater diffraction? Sure?
Yeah.
Diagram 2, right? The smaller the opening when compared to the wavelength. Like, you can put on your phone and take off your headphone.
Yes, sir.
And take off your headphone. Huh? Right? So the second one, I wasn't calling anyway. Right? So the smaller the opening, the greater the diffraction. And we will see that when we come to diffraction and using the formulas, right?
Yeah, I watch it.
And last thing, interference. When two waves meet at a point, the resultant is the vector sum of the individual waves. So for example, if you have a wave, right? If you have a wave here and a wave here, and those two waves undergo interference, right? The interference is the algebraic sum of all points. So adding up here and here, adding up here and here, adding up here and here, and so on. And I'll get a larger wave. Right? These two waves are said to be in what? In phase. And what type of interference we have here? Constructive, right? How you get destructive interference? Out of phase, right? Nice. Right. There are three things, this note, right? There are three things that kind of control the interference pattern. You remember what interference pattern? Daria? What's the interference pattern? What's the interference pattern? Yeah, pattern. All right. I don't know if you all remember this diagram from Form 5, right? I remember that? Right. Whenever you have waves coming out of an opening here and here, the waves will undergo interference.
Yeah.
So there will be destructive and constructive parts. And if you put it on a screen, what is observed?
Like the
So, what is called that?
destructive. That's not good.
Now, the next word. What is called fringes. So on a screen, you will see bright, dark, bright, and so on, right? Those fringes are your interference pattern. Okay? Those fringes are your interference pattern, and it have three things that affects that. Yeah? Sorry? So now, asking what are the three things that affects that?
Distance.
Hold on, I'm gonna see if I can show you in a simulation here, right?
So I don't know.
I don't have the thing anymore. I used to have a diffraction rate and a laser, I don't know, we put together. No, it wasn't the llama, somebody. Somebody that's go up at night. That's seen once in what about the pain into that?
Just under the thing to not. No, but it went.
I want to do what. Yeah.
If I can be an operator.
No, but I didn't go. But I didn't look out.
Alright, watch this here. I'm not sure if you will see it fully here. Alright, watch your all here. Right, watch it here. Watch what happening, right? So you see how the waves undergoing the interference, right? I don't know why we can't get a screen to see everything, but let's make the width here smaller, right? And tell me what you're observing.
But I want that.
Hold on, I'm trying to get a graph to show you that one. Now, you see the screen, man, I'm seeing how to get in. One of these images here is giving the screen.
Exactly the same thing.
Online, you're seeing anything there?
So,
Alright, let's now change in the simulation and hold on. I want you to see the screen. Alright, so watch this here. This one is seeing the fringes. Right? When the light go into the watch here. So when the light go into the double slit, right? When the light goes to the little double slit here, the part on the black is the fringe pattern. You're seeing that?
Yes.
Light, dark, light, dark, light, dark. Right. Look at the focus on the fringe pattern. Focus on the black screen and the light on it, right? I'm going to change the width a little bit. See anything happening?
yeah.
Right? See anything happening? Number one, you might recognize that you're seeing less fringes, right?
Yeah.
And then you might see the width changing a little bit. Right? Let's keep the width between that and let's put the distance between the slits. Let's change it. See how the fringes opening up some more? So the slit width and the distance between the slits affecting the fringes. Let's play around with the wavelength a little bit, right? See if the wavelength affecting it. Watch it get Yeah? Well, yeah, with the different wavelengths mean different colors, right? That's why I'll do that. Right? But watch the fringes. See it again further apart and now closer. So three things that affect it is wavelength, slip separation and distance between slips. There's one more. I don't know if I can move it, but the one for the screen, see that 1 meter here? If I push back the 1 meter, it will also affect the fringes. All right, so there's one big formula that we're going to prove next week on dealing with interference, right? So I want you to remember these 3 factors. Are you okay with that? So but when I say fringe separation, I mean the separation here, right? Right, I mean the separation. Let me just change the color a little bit. Right. When I say fringe separation, I'm referring to this separation here. When I say slit opening, I'm referring to this spacing here. And there's one more thing, but this lab does not allow me to change it. But if I were to move the screen further, it will also affect the fringe separation. Right? So we are going to learn about the 3 factors. What are the 3 factors? Wavelength, separation of the slit, and separation of the slit and the screen. So we're going to take a look at how those 3 factors affect fringes. All right. Nice. I wanted to show you how that will look. Let's just go back to the notes and wrap up, right?
So we have time to do all that?
What's that? Yeah, all we have to do in module 2 again is we have interference, diffraction grating, and lenses. 1 week each.
And physics of the air.
So yeah. And yeah. But we can that won't take long. That's the first thing I'll start with next. So yes, we have time to do right. So we talked about diffraction, interference, right? And I gave you a little note here that the separation of the interference pattern is affected by those 3 things. We will prove those 3 things, right? And get a relationship. Yeah, formula for all of those, right? Right. We know about speed and sound already. Right. Y'all remember the qualities of sound, right? What are the qualities of sound? And quality. What affects loudness? Amplitude of the wave. What affects pitch? Frequency, right? Right? It affects frequency. And quality is a kind of combination of both of them.
Yeah.
But the same note played on 2 different instruments does not sound the same and are said to differ in quality of timbre. Darian, explain quality and timbre. He's a music man.
Quality.
And timbre.
The same note played on 2 different.
Explain that to me now. He's a music man.
Because it depends on like the type of quality. Yes. So like if it's metal,
Yeah.
it's gonna be certain metal.
Right.
And if it's strings,
Why?
because it's have different waves.
Different waves. So you mean you could use different amplitudes,
Yeah.
right? So based on what type of material it's hitting, it'll produce different wavelengths, different amplitudes, different frequencies.
That's why I say different waves.
Very good. Very good. Right. These sounds are not pure notes as they are from a tuning fork or signal generator. They consist of fundamental frequency and overtones, which are multiples of the fundamental frequency. The number and intensity of the overtones determine the quality of the sound. Okay? All right, nice. Did I show you intensity last week? Right. I just want to talk about something called intensity level. So when we go to the air, right? When we go to the air, you would recognize that whenever they're talking about air and the amount of sound intensity it can take, we always talk about decibels. Right? We always talk about decibels. So we need to convert our intensity values to decibels, and this is the formula. Right, so since you all don't read these notes, just write down this now, please. Write down this formula for intensity level. Right, intensity level is equal to 10 log by I over I naught. Anybody know what I naught? Why that's not showing up?
That's under like it. If we are on a soup, and we're not getting it, we are not like we're going. So.
Hold on, yeah. I'll write it here for you. Right, so watch here. So there is something called intensity level, right? Darian, shut up now. Now 10 log I over I naught. So you could take all the intensity values, plug it in here, and convert them to intensity levels. This will be in decibels. This will be in watts per meter squared. Right? What is I naught? Some of you all did this already. What is I naught? What is I naught? 1 by 10 to the minus 12. Yeah, Marquis?
Yes, I was gonna say that.
So this value here is the value for intensity level.
So what's your answer actually?
Oh, you don't think fast, boy.
I'll go to you think those.
Oh, yeah. Alright, so here you'll recognize that with air, right? They don't really have these values. They kind of work more with decibels, right? So yeah, that I some lower script subscript out.
Wait, but what he has done.
Right, just do my favor now. I want you to convert, just try a quick example. Let's take a value, right? There's a threshold of hearing. This value here is a threshold of hearing, right? So let's take a value and find IL from that. Right? Take I is equal to 1 by 10 to the minus 10. Convert this value to decibels. Somewhere again, huh? So basically, how you find the intensity level? Somewhere you get fast. Just plug it in the calculator, right? Put I as 1 by 10 to the minus 10.
So and it'll be like 10 log of 1.
Oh, what's it? What's it? Right, you just plug it in the formula here. So you'll get 10 log 1 by 10 to the minus 10 all over 1 by 10 to the minus 12. Work it out in the calculator and tell me what you get. How much decibels is that? I change them with decibels all over here. Hurry up. How much is that? Much are they at? 20? Yeah. 20 decibels. That's okay? So please remember to go from the decibels, you'll have to just rearrange the formula and find for I, right? Last thing before we wrap up. Last thing before we wrap up, right? Take a look at that diagram there for the human hearing. right? That green area is for normal hearing. Right? If the intensity goes too high, they end up in the discomfort region. And if it goes higher than that, they end up in the pain region, right? So how much, look at the scale, is that, if you look at the scale there, I gave you a scale in intensity, not intensity level, right? So here will be an intensity level of 20, here will be 0, and then you can work out how much here is. 10^2. Right? Just plug it in the formula and you'll be able to get the intensity level up there. Right? But this is for normal hearing, right? What will happen for old people? Darian, Darian.
Was telling me something.
So Darian, well, what will happen as they get older?
Yeah, another thing.
Thing. What thing?
The range will,
The range will decrease, right?
yeah.
So-
Be able to hear the pain will take lower.
Right. So what will that graph look like now? What will the graph look like?
Go down and.
It will, right? So the graph will move down, so it might be somewhere here, and what else? Would it go down as low? No.
Nah.
So the graph might be something like that,
So that way you hear it.
right? That's where the graph will go. Right? So your threshold much lower, so your threshold is much lower, right? And your pain level will drop. The pain level will drop, and you'll recognize that the frequency that you're hearing at will also drop. Okay? Right now your frequency range is here to here. But as you get older, it will get smaller and smaller. That's okay?
Yeah.
All right. So next day we'll continue from here. We're going to focus more on diffraction and interference and refraction. All right. So that's it. You have to log out. I shall see you.